Proxima Centauri b, the closest exoplanet to our solar system, has recently become the focus of renewed scientific curiosity after being linked to mysterious bright flashes. Could this be a sign of an alien civilization? Stay tuned for more. For a long time, scientists and ordinary people alike have been eager to imagine what life beyond our planet might be like. Any science suggesting the existence of something beyond Earth has always been greeted with enthusiasm, hope, and excitement. Then came a turning point, one that redefined the boundaries of astronomical research, when the James Webb Space Telescope delivered clear indications that life may exist somewhere in the vast cosmos. While scanning the depths of space, this powerful and highly sophisticated telescope detected something particularly fascinating on Proxima Centauri b, a distant exoplanet orbiting our nearest stellar neighbor. It observed lights, bright, organized, rhythmic, that were startlingly similar to those of extraterrestrial cities, illuminating the dark side of the planet. This observation raised a provocative possibility. Could an extraterrestrial city truly exist on this distant planet, nestled within a solar system just 4 light-years away from us? The implications of such a discovery are staggering and have generated great excitement and profound curiosity among scientists, researchers, and astronomers across the globe. Many are intrigued because such a finding could be one of the most important discoveries in the history of astronomy and human civilization. It suggests that there could be intelligent beings beyond our current understanding, beings capable of organizing their societies, developing infrastructure, and perhaps even communicating, in ways we are only beginning to imagine. Looking at these distant, sitter-like lights, located an incredible 4 light-years from Earth, NASA engineers are filled with awe and wonder. They ponder how long these lights might have been visible in space, silently waiting for our technology to evolve enough to detect them. It's a humbling realization that for countless years, such signs might have been flickering across the cosmos without our knowledge. David Kipping, an astronomer at Columbia University and an expert in exoplanetary sciences, described the planet where these lights were found as particularly complex. Unlike most rocky planets that typically absorb sunlight and emit energy in the form of infrared radiation, this exoplanet exhibits different behavior. Its unique interaction with its parent star, Proxima Centauri, a red dwarf star, makes the thermal and light patterns on the planet especially difficult to interpret. This complexity is precisely why the discovery made by the James Webb Space Telescope, often simply referred to as the Webb Telescope, is so significant. It underscores the importance of having such advanced observational tools. The telescope's unparalleled ability to capture infrared wavelengths was instrumental in detecting the unusual behavior of Proxima B. These observations are crucial in understanding the atmospheric conditions of the planet. Researchers now plan to continue using the Webb telescope to explore Proxima B's atmosphere in even greater depth. They hope to investigate whether the planet might be habitable or already harbor life. The James Webb Telescope is especially sensitive to infrared light, which allows it to observe what's happening on Proxima Centauri b even at night, when the dark side of the planet faces away from its star. For many telescopes, detecting faint light in the vast darkness of space is a daunting challenge. But the James Webb Space Telescope, thanks to its revolutionary design, is able to pick up even the faintest glimmers of light. This makes it an ideal instrument for confirming whether the supposed city lights on the dark side of Proxima b are real and not merely a fluke or instrumental anomaly. The telescope can detect artificial light in space if it exists within a very narrow frequency band, much narrower than the light emitted by normal stars. This makes its capabilities highly specialized for seeking signs of advanced civilizations. Proxima Centauri b, however, has a dynamic and multifaceted relationship with its host star. One side of the planet remains locked in constant daylight, while the other lies in perpetual night, a phenomenon known as tidal locking. Numerous solar planets capture their star's intense energy, and the resulting spectrum also reflects that light in unique ways. As Proxima b revolves around Proxima Centauri, it experiences a day and night cycle, albeit in a vastly different manner than Earth does. These extreme conditions bring intense heat during the day and much cooler temperatures at night. The planet experiences large temperature variations, mainly influenced by its composition. For instance, if Proxima b lacks a substantial atmosphere, temperature differences between day and night would be dramatic and extreme. Without the moderating effect of atmospheric gases or the thermal buffering of oceans, the planet's day side would warm significantly while the night side could cool to sub-zero or even cryogenic temperatures. This dramatic thermal variation is an area of great interest to astronomers, as it offers important clues about the potential atmospheric composition, or lack thereof, on Proxima b. The James Webb Space Telescope, with its unique ability to image in the infrared spectrum, can effectively analyze the planet's thermal emissions. This provides scientists with valuable information about Proxima B's atmospheric properties and surface conditions. Interestingly, the Webb telescope's orbit around Earth coincides neatly with the orbital period of Proxima B, which allows for detailed observations of the exoplanet's daylight cycles approximately every 11.2 Earth days. If the planet has an atmosphere, the next step for scientists will be to examine its chemical composition to determine its capacity to support life. Signs such as the presence of oxygen, water vapor, and methane in the atmosphere would be indicative of habitable conditions. If these elements are detected on Proxima B, it would significantly boost its profile as a potentially life-supporting planet. Confirming their presence would involve analyzing the light passing through the planet's atmosphere, a complex and delicate task. Although the James Webb Telescope is excellent at characterizing planetary atmospheres, it was not primarily designed for detecting free oxygen, which is one of the most crucial signs of life. The telescope specializes in analyzing variations in the concentrations of water vapor, carbon dioxide, and methane. Despite its limitations, it can also search for other important elements such as ozone, which often indicates a healthy and active atmosphere. As scientists continue to examine the data streaming in from the James Webb Telescope, the search for distant worlds continues. Each discovery brings us closer to answering the age-old question of whether we are alone in the universe or if other life forms share this cosmic expanse with us. It is important to remember, however, that the James Webb Telescope can observe only a limited number of exoplanets, those closest to Earth. For more detailed atmospheric studies, astronomers will increasingly turn to ground-based observatories like the Extremely Large Telescope, ELT, which is expected to begin operations in 2028. The ELT is specifically designed to offer a deeper, more refined look at the atmospheric structures of distant exoplanets. It will provide high-resolution and detailed data on their potential to harbor life, complementing the findings of the James Webb Telescope. Scientists are also eagerly anticipating the operation of other future space telescopes like the LUVOIR, Large UV Optical Infrared Surveyor, and the HAB-X, Habitable Exoplanet Observatory. In the meantime, the James Webb Telescope remains an indispensable tool for the exploration of distant exoplanets. Despite its limitations, the Webb continues to deliver valuable information that could fundamentally transform our understanding of what exists beyond our solar system, both now and in the years to come. Researchers have ambitious plans for space telescopes of the future. They aim to develop advanced technologies that can reduce or completely block out the blinding starlight from parent stars in order to better observe the faint planets orbiting them. It's akin to using your hand to block the glare of the sun in order to see more clearly. By dimming starlight, these future telescopes will be able to more effectively study the faint reflected light from exoplanets, helping to analyze their atmospheres and determine their ability to support life. However, this task is much easier said than done. Blocking out starlight to observe exoplanets remains one of the most formidable challenges in astronomy. Stars are incredibly bright, often outshining their surrounding planets by orders of magnitude. This makes it very difficult to detect the faint light that planets reflect, light that is essential for studying planetary characteristics. To tackle this problem, scientists are developing several groundbreaking techniques. One such technique involves the use of coronagraphs. These devices are installed inside telescopes and are engineered to block out the starlight while allowing the light from orbiting planets to pass through. By carefully shaping the light waves, coronagraphs can significantly reduce the glare from the parent star, making the dim light from the planets more visible and thus more scientifically valuable. Another highly promising technology is the star shade, a massive flower-shaped spacecraft that flies in formation with the telescope. Positioned tens of thousands of kilometers away from the telescope, the star shade blocks the starlight before it even enters the instrument, allowing only the light from the exoplanets to reach the sensitive detectors. This method is especially effective when observing planets located in the so-called habitable zone of their stars, a region where temperatures are just right for liquid water to exist, and potentially, for life to develop. These technologies, however, demand an extraordinary level of precision. For example, the alignment of a star shade needs to be accurate down to fractions of a millimeter, even over vast distances in space. Moreover, these advances must overcome the inherent limitations of space missions, including the need for miniaturization, energy efficiency, and the ability to withstand the harsh environment of space. Despite these considerable challenges, the potential scientific rewards are immense. Successfully observing and analyzing the atmospheres of exoplanets could lead to the discovery of biosignatures, chemical indicators of life. Molecules such as oxygen, methane, or water vapor found in specific ratios could hint at the presence of biological processes, suggesting that life might indeed exist beyond Earth. Researchers are also exploring methods to directly image these distant worlds in greater detail than ever before. Future telescopes may be equipped with advanced adaptive optics systems. These systems dynamically adjust for distortions caused by Earth's atmosphere or slight movements of the telescope, producing sharper, clearer images of distant targets. Combined with starlight blocking technologies, these improvements could allow scientists not only to detect exoplanets but also to map their surfaces, study their weather patterns, and examine their climates. The development of these next-generation space telescopes represents a monumental leap forward in our quest to answer one of humanity's most profound questions. Are we alone in the universe? By redefining and expanding our ability to observe distant planets, we inch closer to the moment when we might find evidence of life beyond Earth, evidence that could revolutionize our understanding of life, of ourselves, and of our place in the cosmos. The search continues, but with every advancement, every observation, and every new piece of data, we move closer to unlocking the secrets of the universe and possibly confirming that we are not alone. As the data from the James Webb Space Telescope continued to stream in, the scientific community entered a phase of cautious but electric anticipation. Conferences were convened, papers submitted for peer review, and an entire ecosystem of interdisciplinary collaboration sprang into motion. Astrophysicists, exoplanetary scientists, biologists, chemists, linguists, and even sociologists and philosophers found themselves drawn into this extraordinary moment. The question was no